Over the past couple of lectures, I've been talking about simple linear regression and how we do or how we conduct a simple linear regression once we're given some data. So I want to go through an example, and it's taken me a while in class to kind of talk through all the different pieces, but I want to use an example to kind of go through and show you that it's fairly straightforward. Obviously, it's a process. There's a bunch of steps involved, but I want to go through and look at an example with you and go ahead and show you what we got. So what you see on the screen is a data set. I mentioned how regression got its start trying to predict the height of children based on dad's height. And so I collected some data. I collected 70 observations, 70 students, and I asked them their heights and I asked them their father's heights. And you can see the scatter plot. And let's say my cursor should probably show through. You can see that on the lower left-hand side, we have some points over here. We have shorter fathers and we have shorter students. And then as you move to the right, you can see that while it's not a perfect relationship by any stretch, you can see it starts to increase. Now, I believe I showed you in class how a lot of these points where the cursor is right now, those are my female students, because females on average tend to be a little shorter than males. Not every single female is shorter than any other single male by any stretch, but there are some trends. But you see that even when you don't consider the sex of the student, there is decidedly a positive linear relationship between the variables. And so what you see at the bottom down here is the Excel regression pronounced. Let me scroll down. There's a couple more down here at the bottom. And I want to just kind of talk our way through it. And so the way I presented in class, excuse me, the way I presented in class, there are 5 steps. And the first step in a regression analysis is to state the model and actually write out the model that you want to work with. So let me go ahead and fill that in here. All right, so I grabbed a pen so I can write y is equal to, and please be kind, I'm writing with my mouse, is equal to beta naught plus beta 1 times x. And we saw in class there was actually a couple ways. If you write it in terms of y, I have to add plus epsilon on the back. Epsilon's our random error component. If you write it in terms of e of y, the expected value of y, or the average of y, the expected value of y is equal to beta naught plus beta 1x. And those are the 2 different ways of writing the simple linear regression model. All right, there we go. Kind of ugly, but you see what we get there. We use a software, and I'm going to come down here in the software. There are my coefficients. Those are my estimates of the beta. So y hat's equal to, the intercept is 10.0, I'm going to make that 10.03, plus 0.83, I'm going to round a little bit, times x. And so now we need to interpret those intercepts and intercepts and slope for me. So the B0, the 10.03, that's my estimate of the beta naught. The B1, the 0.83, is my estimate of the beta 1. And so we want to go ahead and give our interpretations. Now when we interpret a y-intercept, we always have to ask 2 questions. Is it practical? The way you interpret a y-intercept, it's the value of y when x is equal to 0. So we estimate a student to be 10.03 inches. That seems kind of crazy. When dad is 0 inches tall. Well, dad can't be 0 inches tall. That's nuts. So that's not a practical interpretation. And the 2 things you have to ask to determine if it's a practical interpretation or not. Does the value of x equals 0 make sense? Does it make sense for dad to be 0 inches tall? You got to go with x, right? Dad's height is the independent variable. Height of a student is the dependent variable. So that's not a practical interpretation because the value of x equals 0 doesn't make sense. Now, if it does make sense, then you also have to consider, did I sample over a range of values that included x equals 0? You can see in our data set, if it made sense, it doesn't in this case, but if it did, notice our smallest value of x was 54 right here. Our largest value of x looks over here, maybe like 73 inches tall. So our data spanned between 54 and 73. You got to make sure the value 0 is in between there somewhere. Could be the endpoints, but you got to make sure 0 is in there. And when it's not, then that would be another reason for saying that you don't have a practical interpretation. Now, the slope is always a practical interpretation. And the slope is the rise over 1. For every 1 unit increase in x, we estimate y to, in this case, go up by 0.83. So let me type and I'll come back. For every 1 inch increase in dad's height, that's x, we estimate the height of a student, which is y, to increase, because it's positive, 0.83 inches. It's important to get the units of measurement. For every 1 inch increase in dad's height, we estimate the height of a student to increase by 0.83 inches. That's a slope and a y-intercept. The slope will always be a practical interpretation. The y-intercept probably won't be. It could be in some situations, but probably not all. All right, our 4 regression assumptions. The mean of the epsilons is 0. I'm just going to call them e's here, is 0. The epsilons are normally distributed. The variation of the epsilons is constant for all settings of x. And then lastly, the epsilons are independent. Those are the 4 regression assumptions, and you should probably use epsilons instead of e's. I just did it for the ease of use, pun intended. Those are 4 regression assumptions, and then we want to interpret the standard deviation, and Excel calls it the standard error, and so I'm going to look. Let's see, there's a standard error. Let me highlight it here. Standard error 4.84. So the standard error is 4.84. The way that we interpret a standard deviation, we expect most of the observed y values, or I'll say most of the sampled, observed would be another way of saying it. So y values would be student heights to fall within 2 standard deviations. That's going to be 9.68 inches, if I did my math right there, of their least squares predicted values. Now, I'm saying this, they're within 9.68. That's in either direction. So this interval ends up being what? Wow, it's like 19.36 inches wide. That's a crazy wide interval. And that's going to be, you'll see that when I do the confidence interval and prediction interval. At the bottom of the page, you're going to see that that large standard deviation there is going to give me large confidence intervals and prediction intervals. Okay, so that's the standard deviation interpretation. Now we want to go ahead and test the model. So when you're talking about heights and students' heights, the test is going to see about the slope. We're going to test the slope, and you got to figure out what's the relationship. What relationship do you expect to see here? When you're talking about heights and dad's heights, as dads get tall, what do you expect to see? Well, you expect to see, with taller dads, you would expect to see taller kids. I'm going to grab a pen here. So the test that we're going to conduct, we're going to test to see if there's a positive slope. We're going to test beta 1 is greater than 0 versus the null hypothesis, which is always going to be an equal to. So that's what we're going to test. We're going to do a positive slope. If you're working with your automobiles, it's probably the other way, right? You expect higher mileage automobiles not to have higher prices. You expect them to have lower prices. So a less than test would be appropriate. The test statistic, you're going to go to the printout. You go to your independent variable. We go to dad's height, and then we grab the test statistic and the p-value for dad's height. So in this case, the test statistic is 5.78. I'll make that 5.788. And the p-value here, you see that E.07. That's going to be 0.123456199. All right, we move that decimal over 7 places, so you get 0.0000199. However, that's a two-tailed p-value, so we're going to split that in half, which is 0.0000199 divided by half is going to be 0.995. It's really, really small. But this p-value that you see on the printout, those are always going to be two-tailed p-values. So you got to make sure you split whatever p-value you're looking at in half. And again, that's going to be scientific notation. E to the minus 0.7 means move the decimal 7 places to the left. And then you got to split it in half. And then our conclusion is going to be, let's go here. Let's go down to the next one and come over here. Our conclusion is going to be, well, the first thing we got to do is pick an alpha. I'll pick 0.05. We reject H naught. There is sufficient evidence to what? Well, we're going to say beta 1 is greater than 0 when we do a test hypothesis. When you reject, there's sufficient evidence to indicate the alternative is true. Now write that in the words of the problem. There's sufficient evidence to indicate that there is a useful positive linear relationship. Positive, spell it right, Mark. Between student height and dad's height. At alpha equal 0.05, we reject. There's sufficient evidence to indicate there's a useful positive linear relationship between student height and dad's height. The r squared in the printout is given as 0.33. The way that we interpret r squareds, again, let's line this up so it looks pretty. This is the percentage of the variation in the sample data that we can explain. We can explain 33% of the variation. It's called the y-bar variation. The variation in the sampled student heights around their mean using the linear relationship with dad's height. That's our standard r-squared interpretation. All right, so we test the model. We test to see if the slope is positive in this case. Again, you got to consider whether you're doing a greater than test or a less than test. And I mentioned in class, when you're doing a test in simple linear regression, you should be doing a one-tailed test. A two-tailed test is not appropriate, because when you do a simple linear regression, you should have an idea what the relationship is. And then, so we conduct the test, making sure we're aware of the fact that we have a two-tailed p-value there that needs to be split in half. And then we interpret the r-squared value. Now we're going to use, step 5, we're going to use the model for estimation and prediction. So we are 95% confident that both the prediction interval and the confidence interval for E at Y, that's typically how I say it, prediction interval for Y, both start the same way. We're 95% confident that. And now the easier one typically is the Y. Y is the height of a student. But when you talk about the prediction interval and the confidence interval, you got to get more specific than that. It's not just the height of any old student. It's the height of the student, and in what we're working with here, it's the height of a student whose father is 70 inches tall. We're 95% confident that the height of a single student, that's Y, whose father is 70 inches tall. Oops. Okay, we're 95% confident that Y, and when you mention Y, the height of a single student, you got to mention the value of X that you're working with, because as X changes, all the numbers change, and then you use the numbers. Will fall between, now you got to choose the right ones, right? When you're working with an individual value, prediction interval for Y, 53 point, we'll just make that 53.4, and 77 point, we'll make that 77.9 inches tall. I'm choosing these numbers right. Let me highlight them right there. The prediction interval for Y. That's how tall I'm predicting my individual height, the student's height will be between 53.4 and what is that? 53.4, that's what, 4 foot 5 inches? And 6 foot, almost 6 foot 5 inches. It's a really wide interval. Why is it so wide? Well, our standard deviation. Remember how wide the standard deviation, how big the standard deviation is? We expect to predict it within 9.68. Look how wide the interval is. They go hand in hand. The standard deviation is your first taste of how useful the model is going to be. Now, what I'm going to do is I'm going to copy paste. I'm going to do this. Now, you got to be careful doing this, right? Because when I'm talking about E of Y, we're 95% confident, not the height of a single student, the average height of all students, get your plural right here, whose fathers are 70 inches tall, right? Because you're not just talking about a single student here. You're talking about, think of all the students out there whose fathers are 70 inches tall. The average height of all students whose fathers are 70 inches tall, and now these numbers are going to change. They're going to get a lot closer together. We're going to go 66.9. I'm using the E of Y numbers now. 66.91 and 69.34. I'm not trying to predict your height here. I'm trying to predict the average of all the heights of students whose fathers are 70 inches tall. Different beast. We got Y, we have E of Y. You got to be able to work with both. You got to be able to see the difference between the two of those. But those are the steps that are necessary in a test of hypothesis. Let's see if I can get this all on one page. Close, so close. Start with our model, then we do our beta interpretations. We make our interpretations of them. Again, be careful with B0. It's usually not practical, but it could be. Know your assumptions, interpret the standard deviation. Be able to tell me which side or which direction the test is. Make sure you can identify the correct p-value. You got to split it in half usually. Make your conclusion, interpret R squared, and then interpret the confidence intervals for E of Y and Y. And that's how we do a regression analysis. So I took over almost, it's probably somewhere between, what was that, 2 hours, 120 minutes, 150 minutes maybe. You know, between 2 and 2.5 hours to go through the regression, and it took me, I'm on, what, about 16 minutes now. So hopefully that makes sense for you, and you can recreate this with your automobile data. Get your printouts, get your, and I shouldn't say automobile data because it depends what semester you're looking at. Sometimes I use automobiles, sometimes I use homes, sometimes I use apartments, but your project for data set. Good luck.